So Keshav and I did our project on the Behemoth roller coaster in Canada, and how this is going to work is we have two slides after this that are diagrams of the roller coaster, that a photo of it in like scale drawings to show how we determined the corresponding heights. And then after that, we have a video that shows like a first person view of someone actually riding in the roller coaster. And then we have the next slide, which is information on G force and other um, key measurements for our roller coaster. And then we have a table that shows the velocity of the coaster at 7 points along the path using the law of conservation of energy. And then lastly, we have a graph um, that will show points, and it's going to show the force in newtons that an actual rider on the roller coaster would experience as the ride goes on.
This is the drawing I used, and as you can see, there are points labeled on the drawing with the heights. And this is basically a scale drawing of it, so it's in the proper view. And as you can see, these points correspond to the points here. And G1 and G2 are basically the points where I calculated the G's. And this is the video of the roller coaster. And here we have some basic facts. This is the G-force calculation. And this is basically a quick check to see if it actually matches. The max speed is given on Wikipedia. And the total energy kind of matches with the potential energy at the greatest height, which is the total energy there. It's only a difference of 5 joules times 3,000 because of the mass. And this is the G-force. The radius, okay, so there is no vertical change in the first curve here, which is at 3. So basically, using Google Maps, you can measure the distance, which was 20 meters from one end to the other of the circle which forms the curve. And then the radius is obviously just half of that. And using the velocity found with like the energy equations, you get there's 4.8 G's experienced, and the other curve is actually vertical, so that involved that. It was a dip, so it's plus G before dividing by G.
Next, we have a table um, with 8 points, and we have the height, the total energy, the potential energy, kinetic energy, and then the velocity of the coaster in meters per second. So basically, what is going on here is that starting from the first point, that's the highest point, and then from there, every subsequent point gets lower and lower until it reaches 10 meters from the ground. So obviously, based on the conservation of energy, the total energy in joules is going to stay the same at roughly 2.05 million joules. And since the height of the person in the roller coaster, that's going to be consistently decreasing. So we have the potential energy at the start, it's all potential energy, around 2 million joules. And then from there, it just steadily goes down until it reaches about 294,000 joules. And the same goes in the opposite direction for kinetic energy, because it starts off at 0 because it's not moving, and then from there it just increases as the roller coaster is going to gain speed from 0 meters a second. It's going to go up and up until it reaches a maximum of 34 meters per second at the very end. And next we have a graph that's going to show the force in newtons that the rider experiences as the roller coaster progresses along the track. So for distances, we have 250, 700, 1000, and 1315 and 1750 meters from beginning to end. And then um, basically the force as shown in the graph is not really going up too steeply. It's steadily increasing over time. And basically how this force was determined is that every single point on this graph is showing the roller coaster at like the very bottom of a dip. So the lowest point after it goes up and it goes down, it's going to be the lowest point on that dip, and that's all going to be 10 meters above the ground. So um, the height is always the same, and then the formula to use that we used to calculate the force was v squared over r plus g, all of that over g, and the v squared is always the same. And then the only thing that changes is basically r, and then we use that to calculate the force in newtons for each of those points on the dip, for all those 5 points on the graph. And then finally, for sources of error, we have the first source of error, which was a small um, discrepancy in the energy, because using the actual maximum speed, the total energy we got was about 2 million joules, 2.07 million, but then um, using the actual total energy, given the starting height, which was about 70 meters, then it was about 0.8% off, with the total energy was only about 2.05 million joules, but it was a really small, less than a 1% discrepancy in the energy given those two methods of calculating. And then the second source of error was calculation of the G's, because basically when the G's that the rider experiences, when that was calculated, we assumed that the dips at the lower points of the roller coaster, we assumed that those were circular, but even though it was rounded, it wasn't 100% circular. So that could have caused a little bit of a discrepancy in the G-force calculation. And then for the distance along the track, that was we found that using Google's they have a measure distance tool from satellite view, um, but that was like, it's probably inaccurate. It was sometimes hard to tell what the actual distance was, but even so, it wasn't on the graph. The slight differences in distance wouldn't be, it would not have a big effect on the actual shape of the graph. And that's it. Thank you.